Okay, so in this video, we're going to be talking about the ideal gas model. And we want to be able to explain or predict physical phenomena related to gases in terms of the ideal gas model. And to account for the properties of gases, scientists have devised kinetic molecular theory, which is something we've already talked about in this class. And as always, chemists explain macroscopic phenomena in terms of particulate level behavior. And that's what we're going to look at today. We're going to look at the main features of this model and how it applies to our understanding of gases. So let's just go through this. This is going to be a fairly short video. The first feature of this model is gases consist of particles moving at any given instant in straight lines. So this is kind of the same picture we saw before, where gas molecules, this is a particulate level view, are zipping around in this container, and they do so in straight lines at any given instant. All right, so they're just kind of moving. I'm going to attempt to draw this in straight lines. Okay, they're not moving in zigzag lines like my drawing would suggest. Okay, they're moving in straight lines in the container. Maybe they hit the wall of the container and then they bounce off, but that's a straight line that's illustrated here at any given instant. When you look at the gas, it's moving in a straight line. It's not zigzagging all over the place, okay? So contrary to what my drawing would say, gases are moving in straight lines at any given instant, okay? That brings us to our second characteristic of this model, is that molecules collide with each other and with the container without losing total kinetic energy. Okay, so that's just kind of illustrated here. So this little equation, so E1 is equal to E2 is equal to E3, okay? So again, they're not losing any kinetic energy, total kinetic energy, when they're colliding with each other in the walls of the container, okay? Third feature of this model is that these gas molecules are widely spaced apart. And the cartoon is actually, how should I say this? The cartoon is probably not illustrating this as well as from the perspective of a gas molecule, that they're really far apart of these gas molecules from their point of view. So they're widely spaced apart, and that means that the attraction between molecules is very low, okay? So they're not very attracted to each other, and that's actually a point that we're gonna see later. So they're widely spaced, and the actual volume of the molecules is negligible compared to the space that they occupy. So what I mean by that is if we were to gather all of the oxygen atoms together that are in the air and put them in a, in a little box, let's say, that fit their volume, that volume of all the molecules would be really small compared to the volume of the room that they're in, or compared to the volume of the container that they're in. Because again, these gas molecules spread out and uniformly fill the volume of the container. And you go back to the last video and look at the example of like the piston, where even though there was a big volume of the piston, the gas molecules were spread out and they filled that volume uniformly, okay? And then so finally, these gas molecules behave as independent particles. And I already said this, but because they're so far away from each other, the attractive forces between them is negligible. And again, this is something we talked about a little bit when we introduced kinetic molecular theory, and we talked about states of matter in chapter 2. So this is just kind of reiterating that same point, that in the gaseous state, the molecules aren't very attracted to each other. All right, so if I could summarize, an ideal gas is a model of a gas that is constructed of identical particles that occupy no volume and exert no force on one another. When the particles interact with one another and the walls of the container, they do so with no net loss in kinetic energy. Okay, so that's kind of the idea, that there are these particles that occupy the volume of the container and exert no force on one another, attraction or repulsion. And when they interact with one another in the walls of the container, they do so without losing net kinetic energy, or their total kinetic energy. Okay, so that's it for this section. And after this, we're going to move on to measurement of gases.